Thank you. Well, thanks. Great to actually see so many people here. And this is the last day. We'll have, well, you can always optionally wear masks because most other states in Germany introduced the abolishment of masks today, but Bavaria did it as of tomorrow. So this is about some work that we've actually worked for a long time on. Okay, it's the first publication on this. So this is basically a story, and I can tell you the background. The background is that the motivation is to arrive at very high performance automatic differentiation that runs on GPUs. And so we took a stab at looking at it from a fundamental point of view, because the kinds of problems we're looking at is actually right now very high dimensional problems. So when you think of an N and an M, you should think of it as like, millions and between 1,000 and a million, maybe bigger. And some machine learning models a lot bigger. And also think about it in terms of really what's going on. Differentiation, this is probably not unfamiliar to most of you here, is actually there's a lot of work that looks functional analysis, but actually the rules we're using are very algebraic. Okay, so you could think of it as like, identifying rules that are sufficient to find out interesting properties, differentiation, stochastic gradient, applications, various kinds of things, such that, like we'll have Hilbert spaces later on and, analytic functions, whatever, are a model for it. But frankly, the thing that, from a category theoretic point of view is like, these rules are probably going to look familiar and applicable with other models, okay, even discrete models. So, let's just get started. So just, so the basis of the approach is the following. It's like, let's try to formulate functions, right? So there are going to be homomorphic or, analytic functions, the ones that you write down in Python, right? So let's say I'm not usually writing down analytic functions in Python, but you're writing down functions that operate on real numbers. Very often you force to actually write them down to operate on floats, but let's just pretend they're real numbers now. And then you have some kind of effects in the middle of it, like printing something or doing some of the strings or whatever, or taking a branch, going into one branch and then doing something. But you can think of it as like you're executing the steps that operate on the values you're interested in, inputs, the real numbers, and you focus really on those, and you'd like to actually see what is, when I jiggle some of the inputs, what's the jiggling effect it has on the outputs. Or very often, actually, it's much more popular application of what if I jiggle one of the outputs, how does it jiggle on the inputs, okay? So this is basically a story about actually explaining that in an arbitrary dimension. So this is in principle applicable to infinite dimensional spaces. So just to set the stage, since I don't know all of you personally, I'll take the privilege of assuming you know nothing, okay? And then those of you I know will complain to me bitterly later on about all this kind of introductory stuff, okay? But hopefully it's going to be interesting anyway, okay? So if you just look at, the definitions of various derivatives we have, they're all actually, if you look at them, they're actually all the same, okay? So the ones you learn in school is the upper one. I call it, I'm German, so I have to call it Leibniz. So, I only use the dot notation. Sorry about that. There's kind of a moral obligation. So you have a scalar function that has all of, dimension 1 to dimension 1. This is about, wow. So, but then it says like, you say this is, A is the derivative at X. So remember, this is not a symbolic derivative. This is saying like I'm giving a particular value X, like 25. I'm asking you, what's the value? Is it 27 or 29? That's the derivative, okay? And then the function from the X's to the A's, that's the derivative function, okay? So let's be careful about this. And very often in mathematics, we're very, very eager in getting a symbolic representation of this one as an expression, not a very expression, okay? But in principle, it's just a function, And let's just think about that. So it says like, you jiggle a little bit, and then you try to find something that's a linear approximation. Well, actually, it's an affine approximation here, right? So it says, it's basically f of x, and then some kind of deviation from dx by a linear factor in this case. In a Jacobi fashion, where you're going to n-dimensional functions, it's the same thing. But the thing that confuses lots of people, because actually, is the scalar product here is commutative. This is sort of like an unfortunate accident, okay? So what really is actually going on here is more like this, where you say this is, well, it's like a vector now, and I'm taking an offset vector, a differential vector, and then I'm saying like, well, can I approximate the difference between f of v and f of v plus w dv by a matrix. And the matrix is actually just used really as a matrix. And this is important. So if you're a computer scientist, you might think of a matrix as a two-dimensional table, which is of course not true, right? Because matrices are not used as arbitrary two-dimensional matrices. They're much more constrained data type. So a picture, an image, with dots and pixels on it, that's also two-dimensional, but that's a different data type, right? Because you have different operations on it. So the thing is, like, this matrix is really to be thought of as saying the only thing I'm ever really going to do, well, apart from the fact we're going to do some transformations on this one, is I'm going to apply it in the sense of apply to a vector. Maybe I'm going to pose it with a matrix that's basically the right same thing. So this is matrix vector application, right? So and this thing is really born together with the M, okay? So, well, it's bilinear, which means like, anyway, but so you have this matrix now. That's a Jacobian. And I'll try to also point out to you is like, okay, now we have the Fritz, or sometimes, generalized total derivative formulation, which is subsumes all these because it says like, well, it's not just reals and reals to the nth power. And it's basically saying like, what's really going on here? It's like we got a vector space with sufficient structure. So I'm not going to even go into this one, okay? I'm just like, sufficient structure to interpret the formula that I'm writing down here, okay? And so then, the derivative then is a linear map, a linear function, which is usually called linear operator. It has to be continuous and all these other things, but it's linear map, right? It's a function. And then, the definition is that it should be an H here. I'm sorry about that. So it says that it's the same thing again, and then, it's the linear map applied to the dv, which is this differential I applied to it. Now, if you look at this, this subsumes everything up there, because if you just do a Haskell section, wonderful notation, just put a parenthesis, open paren here, and a close paren there, okay? And you see, oh, that's a linear map. And indeed, M applied to is the Fritz derivative, okay? But it seems you have forced me to write that derivative down as a matrix. And the thing is, like, if you think, like, is that really a wise choice? Remember, n was at least 1,000,000, m was something like 1,000. Is it really necessary to operate on matrices, which is probably what everybody here, I did certainly, learned in the name of linear algebra. Years later, I realized I hadn't really learned linear algebra. I learned a little bit about matrix algebra, okay? So, so maybe these are too big. Maybe we can actually represent them smaller. Okay? Also, we need to do some operations on these because we're not really interested in this thing here. We're actually interested in intuitively, the upside down thing, So the transpose of the matrix. So this is the story of this one. I have some other examples of how this goes, but this is what I would say the AD view. Okay, when people go out and say, "Oh, my differentiation is way different," that's not symbolic differentiation. It's not finite differencing. It's not symbolic differentiation. It's completely different. Okay, and I believe that's due to taking the Gateau derivative, which is a generalized directional derivative, as the fundamental notion of derivative. And the story is why this is so beautiful is here. First of all, let's define it. It says that we have a derivative where it's actually called a differential. The differential dy is a function of two inputs, very important, but not accidentally also called v and dv. So it's the vector v and the differential, input differential, the offset, whatever we call it. And when I say differential, I don't mean it's kind of a magic, infinitely small things. I mean just a vector, okay? That has a certain size, okay? And then, the differential is like, as you can imagine, which is like you take a linear t, and you say like, well, what if we go t steps away in the direction of dv, right? This is what this is. This is scalar multiplication. T is a scalar. So we just say I have a dv, and then I'm saying, okay, if I go now in the direction of dv, and what's the difference to, that value to the v value? And then and then I'm kind of saying like, if I go one step away, in the direction of dv divided by t, the length of t, then I'm trying to get this kind of like arbitrarily close, which is like, making t smaller and smaller until I get this value, okay? So now we can define a function. So think of it as like this, well, function, what is a function? It's just an external thing, right? Think of it as like, being presented in some kind of programming language, okay? So, and then someone has given us a programming language and says, okay, please interpret it, okay? Which means like, here's a programming language for defining analytic functions, here's primitive functions and, composing and doing parallel stuff and so on. And then you say, okay, I write an interpreter, okay? And then the output's the value, okay? So then you have this interpreter. Actually, maybe, if you, like Martin, you say interpreter is too slow, we'll just do a compiler. We'll have a compiler, okay? So you'd say like, well, let's now define a related function, which I call a FAD function, which is accidentally, it stands for forward mode AD, okay? And then we say like, well, okay, given the term, this program given, now I'm not giving it one input, I'm giving it two inputs, namely a v and the dv. In our case, it's just from the same vector space. And then returning there, the normal value. And, well, they got two differential, okay? So, well, that's what I want to compute. I want to get a computation or an integration of this function that does that. Then actually, this is the critical thing that makes it beautiful and simple. It says that the composition, so this is in, think of this is in set, this is a normal composition. It's mapped into a category that has also, it's also in set and has normal composition. Okay. So for a programming language person or a programmer, it means like, wow, I have commands here, do F first, then do G next. And how do I interpret that with non-standard data? With this one, well, do G first, no, do F first, and then G. You don't have to do anything, right? You just have to make sure that when you interpret the function over dual tensors, I'm calling dual tensors because usually it's called dual numbers, that's for the reals, and dual vectors, that's for vectors, of rank 1, tensors rank 1, and dual tensors are basically these beasts. Okay, so, and this is actually what the essence of like things like TensorFlow, Pyro, PyTorch, whatever, are presently used. So they operate on these kinds of data. And if you have K, that's a tensor of rank or order K, depending on which terminology you choose. So, here's an interesting thing. It says, use your existing compiler interpreter program that defines F. If you've implemented it well, you have a nice implementation, an abstract data type. It says, what are my numbers and tensors, right? You just, which operations can apply on this one? You call out functions in your implementation on this one. You swap in a corresponding implementation with dual numbers, vectors, tensors, and you already have a compiler, okay? Let me just run it. This is actually why forward mode AD is called efficient and easy. It's the reason why you can run any kind of program, run a Fortran program, a C# program, or Python, you can just run it and say like, as long as you make sure that, in a NumPy library, whatever, in the bottom of it, I'm just using these dual, these, well, they're in some sense dual, but it's two component representations. I already can generate these things. So, because then, if you compose it, you can see that at the end, you get this differential. Okay, so you have a program that executes one step after the other, you get this differential. And the applications, as I said, please ask me later, they're new ones. But now we need two inputs. This is actually the thing is like all of a sudden, before we could just execute V. Okay, we just take a function F, we take a value and boom, it would kind of run away the program, okay. Also, the categorical, doesn't highlight a very important part, which we had in the Frege derivative, because the Frege derivative says that this thing here, this function here, is not just a function from V to W, it's a linear function. It's always a linear map, okay? So that's hidden here, because this F prime, which takes two inputs, Got two derivatives are basically this, and if you take a partially evaluated version of that, or a curried version of that, and partially evaluated, you get a Cauchy derivative, okay? So why not do that? And that's exactly the story here. We're going to go. So we'll make this composition a different composition, but it's going to be just as nice, you could say. It's just not going to be trivial, okay? In terms of composing two functions, turns into composing the functions as they are. All right, so let's set the stage here a little bit. So Hilbert spaces. What is a Hilbert space? It's just a set of values together plus scalar multiplication 0 that has the proper properties and has an inner product, which you write with this dot notation, kind of unusual. It's kind of indicative of a dot product, which is actually what the inner product is in the Euclidean space. Okay, and as I said, it has sufficient limits to make this go through. Now, what we have here is like a construction of spaces. I use like this empty one is not really important. K stands right here in this setting and on paper for the real numbers. That's just the field, the underlying field as a vector space. Then we have direct sums and tensor products. And both are actually interesting, important of generalization we offer in this paper. So the direct sums are basically the generalization in this setting of both, tuple-like vector spaces where the vector space here depends actually on the index. The vector space here is just a dependent, it's like, the index is 1 and then there's another index n, but in principle, this could be anything. Also tuples, but this is a very simple and very common way of representing using dependent types or these sum types in programming. And it also contains basically copars, which stand for arrays. Okay, so it means that written here it's like it's just a vector space you want to, and then you say like I'll take all the maps. Well, in this case, with finite basis, finite support, all the maps from X to the vector space, okay? Common example would be X is the initial segment from 1 to n. B is, the primitive field. Well, that gives us just the normal vectors. And tensor products are actually very important here. They're usually formally defined to be something that has a wonderful, universal property. And the universal property in this case is like it's the universal bilinear map. Linearity, I hope you remember from vector spaces. So this just means then, but this is actually important to point out. Well, this is computer science, so the representation of vector spaces play a major role. There's many isomorphic tensor products, but we use this one as the kind of canonical representation for vector spaces, which means like it's a constant 0, it's a symbol 0, it's a symbolic operation, so it's like a term, right? So it's a constant time. All these operations are constant time, right? Plus this one and the tensor product, okay? And they're treated, I'm just careful to say, like semantically, of course, we treat the modular vector space axioms up there, and these defining equalities, which basically say it's bilinear, okay? Questions on any of this setup? Yeah.
So you're saying that you don't actually reduce by these equations or anything to a normal form?
Exactly.
Yeah.
Wonderful question, Max. Basically, the whole, several of the talks, and I think Nicholas will be one of them, is basically do not normalize. I mean, this is actually what we're saying. Don't normalize, okay? You're going to pay dearly, literally, in terms of performance. So semantically, we have to make sure that what we implement is coherent with these equalities, but we very often go through the syntax and do various kinds of things. Yeah.
Question. If I remember correctly, that tensor products don't even normalize, right? Like there's no canonical representation of an element. I don't think.
Yes, it depends on actually what you mean by normalize. If you allow, for example, a normal form to be unique modulo, for example, commutativity, okay.
Yeah.
Then it would actually normalize, and well, actually also the commutativity and associativity. Okay, so it's like you just basically say there's an order.
Ah, wait, maybe for vector spaces it actually does. I don't know, I was just confused, maybe if it's not.
Maybe the same kind of thing for vector spaces is. But yeah, they're not normal. I mean, they're not like a unique term. Okay, so very important. The general theme is like there's lots of different terms we have, and they're semantically denote the same element of a vector space. But we operate on the terms on the, and we just have to make sure when we operate in the functions on those that they preserve the equivalences basically they're written down here, so they're well defined. Okay. So here's actually the first result we'd like to present here is like, here's the differentiation calculus. It says if we have a language that has this, sequential composition, functional composition, it makes it possible. So think this as a combinatory language in the sense that let's not worry, because it's very nice not to have to worry about variables, free variables and lambda bindings, local bindings. So it has also constant functions here. It says like, given any kind of value, I'll return W. So this is the function here. Okay. So this is a constant function. Any constant function like this, it says like just ignoring the input. Okay. Then using the section notation before, we had that if you take bilinear, this means bilinear function. We say, well, this is only true if it's bilinear, right? Then you could say that the curring left and curring to the right, they both yield linear functions, right? That's the definition of being bilinear. So the derivative here says it's a generalized product rule. It says that you take an input of UV at UV, then this is a linear map. This is the linear map plus of this linear map and that linear map. And that linear map says take the first components of the, you basically think of it intuitively, you get a du dv as an input, right? So this one says take the du part and then apply the diamond v function onto it. And this one is basically doing the other way around. So if you look, it stares very hard, you can see this is generalized product rule. Very often not stated. And then we have, well, this one is actually quite confusingly simple. It says like a linear map, but actually totally obvious. A linear map, and you want to take the derivative, that's just the linear map itself. Okay? Because it's at any given point, to deviate away with dv, that's just applying h to that dv. Okay. And this is a very complicated way. It's not complicated, but it's highlighting the use of this one here. But this is a way of writing down a rule for parallel composition. So the contributions we'd like to claim here is actually highlighting that there's a rule for general parallel composition here. In practical applications, people very often will argue, look, every parallel application of something I can decompose into a sequence of primitive operations, okay? And then this is good enough, okay? Now that's good enough if you believe in a sequentially executing world, okay? But that's not what you want. So basically you want a rule that says like, basically I have this kind of parallel vector or matrix there, I'm gonna need to take a derivative with respect to all updates to all of them at the same time. And then, I want to get the result at the same time. This is rule basic expresses this. So 3 rules for basically multilinear functions. So with composition up here, it means like for polynomial compositions of primitive functions, and primitive functions would have to be added as a dictionary of derivatives. Okay, so yeah.
What is the triangle?
Yeah, that's the zip apply function. This is actually one that you need here. So the triangle is curiously written like this. I don't know why. Sorry about that. Something with macros went wrong here.
Yeah.
My mistake, of course.
This is the triangle, right?
This is supposed to be the triangle, right? So it's a zip apply, we call it. Okay. So it takes one of these functions, which is like, usually this is a special case of that one. And it takes the corresponding, input, and then it just zip applies it to it. Totally means like, the derivative here, the derivatives here get, because here you get derivatives here, they're all linear maps. Okay, so they need to be applied to something as long as they're linear maps. Well, they need to be applied to a vector. This is a vector, right? So, need to apply by, component
I
wise.
was confused because I
Yeah.
wasn't finding.
No, sorry about that. Yeah, no, that would confuse me too. So now it's the last part. Do I still have a couple minutes?
Yeah, like 5 minutes, including questions.
Oh, okay. All right. So the adjoint of linear math is basically something computes in the reverse direction. Intuitively, just think it was like, I can take a linear map, I can, move forward direction, and then I can also compute backwards. And the interesting thing is you can not only do that for invertible functions like, bijections or isomorphisms, but you can do it actually for all linear functions. So the definition is that this must hold. In the paper, it's explained actually as a way of looking at this one as basically representing, continuations, linear continuations in, by actually just they're dual vectors. So have an efficient representation of continuations. And then you can basically just take an output of something and push it back in this fashion, okay? So imagine a linear map, as I said before. That's easy. If you've given a matrix, that's just the transpose. So sometimes, you hear a transpose, you hear adjoint, you hear emission adjoint, whether it's a real or complex, whatever. But it's basically transpose and adjoint is roughly the same. But the standard approach of doing this, now imagine now you're in a situation, and then look at the paper I'll mention in the end. This is actually the core challenge we have in automatic differentiations. We're not interested in linear map, we're interested in the adjoint of the linear map, okay? And then the core representation, the representation is we represent linear maps as matrices, okay? And then we form transposition to implement the adjoint. But that's a bad idea for high-dimensional vector spaces. In the adjoint of IDs, for example, the identity. Now, if someone says, oh, here's the identity, I'll give you a representation of the adjoint of the identity is like, it's a 1 million by 1 million matrix. That's not a good idea. Just say it's the identity, right? So and there's actually, dense matrix representations that have very, very complex representation. So use symbolic representation. Basically, we have a calculus then that says like, look, if you have x and y here as finite sets, then the transpose of the relations literally is actually also at the set level. Corresponds to the transposes at the linear map level, at the adjoints of the linear map level. So it's just transpose this one, familiar composition is reversed. And here you can see that once you get into basically the representation of values as in our case, we don't only have matrices, but with the tensor products, you can do a transpose operation on that symbolically. And the injection here is projection, and basically it works like this. This is a very important operation. It's the one I mentioned before. If you have a function that takes a relation and moves it up and interprets it as a linear map. So these are very often used as index manipulations in array algorithms. Well, the adjoint is simply the transpose of that relation. So these are, and this is actually a core operation that we're using here, which is a representation of matrix multiplication, but on tensor products like this, which is very, very efficient for tensor product representation. So I'll finish up by saying, what do we get in total? There's adjoint affine interpretation, which means like now you can actually find a 1R thing here, which computes a pair, namely the output and the adjoint in one fell swoop. Okay, when you get there, you need to have a representation, a symbolic representation of the H, and then you get a symbolic representation of the adjoint in this fashion, independent of actually how high the dimension is. So adjoints, you get cheap gradients. This is the holy grail of the 1970s, and still was the holy grail of machine learning then later in the zeros. So using derivative to compute gradient requires application of basis vectors. So forward mode is not good. Using the adjoint to compute the gradient requires only one application of a single basis vector. So you can do this. There's more paper. There's more information on the paper, like relation derivatives, and there's expression smell. There's expression smell, yes. Actually, this as well as it's really hard to debunk, but it's actually easy to see. It's no reason to have symbolic differentiation go through also this kind of affine interpretation to be done both as an automatic differentiation or even doing symbolically by partial evaluation by taking the x input as symbolically. And there's examples in there, for and showing actually advantages of tensor decomposition. Thank you. Sorry. Yeah, thanks.